Relativity. The fact that light travels at a finite but very high speed was first discovered in 1676 by the Danish astronomer Ole Christian Rombier. If you observe the moons of Jupiter, you will notice that from time to time they disappear from sight because they pass behind a giant planet. This ellipse of Jupiter's moon ought to occur at regular intervals, but Rombier observed that the ellipses were not evenly spaced. Did the moon somehow speed up and slow down in their orbits? He had another explanation. If light travels with infinity speed, or you can say infinite speed, then we on Earth would see the ellipse at regular interval, at exactly the same time that they occurs, like the ticks of a cosmic clock, since light would transfer any distance instantaneously. This situation would not change if Jupiter moves close to the Earth or the further move it. Now imagine that light travels with infinite speed or finite speed. If so, we will see each ellipse sometime after it happens. This delay depends upon the speed of light and on the distance of Jupiter from the Earth. If Jupiter did not change its distance from the Earth, the delay would be the same for every ellipse. However, Jupiter sometimes moves closer to the Earth. In such case, the signal from each successive ellipse has less and less distance to travel. So it's a transitive progression earlier than if Jupiter has remained at a constant distance. For analogous reason, when Jupiter is receding from the Earth, we see the ellipse progressively later. The degree of this early and late arrival depends upon the speed of light, and this allows us to measure it. This is what Rombier did. He noticed that ellipse of one of the Jupiter moons appeared earlier at those time of years when the Earth was approaching Jupiter orbit, and later that those times when the Earth was moving away, he used his difference to calculate the speed of light. However, his measurement of the variation in the distance of Earth from Jupiter were not very accurate. So his value for the speed of light was 1,40,000 miles per second compared to the modern value that is 1,86,000 miles per second. Nevertheless, this Rombier achievement, not only in proving that light travels at a finite speed but also in measuring that speed, was remarkable, coming as it did 11 years before Newton's publication of Orbisia Mathematica. A proper theory of a propagation of light did not come until 1865, when the British physicist James Clerk Maxwell succeeded in unifying the particle or the partial theory that up to then had been described the forces of electricity and magnetism. Thought both electricity and magnetism has been known since ancient times. It has not until the 18th century that British chemist Henry Canvet and physicist French scientist such as Charles Augustin de Coulomb established quantization law governing the electric field between two charged bodies. A few decades later, in the early 19th century, a number of physicians established analogous law for magnetic forces. Maxwell saw mathematically that these electric and magnetic forces did not arise from particles acting directly on each other. Rather, every electric charge and current field creates a field in the surrounding space that exerts a force on every other charges and are located with that space. He found that a single field carries the electric and magnetic forces, so electricity and magnetic are inseparable aspects of the same forces. He called that force the electromagnetic force, and the field that carries it is electromagnetic field. Maxwell equation predict that there would be a wave-like disturbance in the electromagnetic field and that these waves would travel at a fixed speed, like ripples of a pond. When we calculate this speed, we found it to match exactly the speed of light. Today we know that Maxwell waves are visible to the human eyes as light when they have a wavelength of between 40 and 80 miles of a centimeter. But what is wave? A wave is a succession of crest and throat. The wavelength is the distance between wave crest and throat. Waves with wavelengths shorter than those of visible light are known as ultraviolet rays, X-ray and gamma rays. Waves with longer wavelength are called radio waves, a meter or more. Microwaves, infraradiation, etc. Maxwell theory implies that radio or light waves would travel at a certain fixed speed. This is what different to reconcile with Newton's theory that there is no absolute standard of rest. Because if there is no such standard, there can be no universal agreement on a speed of an object. To understand why, imagine yourself again just playing ping pong on the train. If you hit the ball so at the front of a train with a speed your opponent measured to be 10 miles per hour, then you will accept an observer on a platform to perceive the ball moving at 100 miles per hour. The 10 it is moving relative to the train plus the 90 the train is moving relative to the platform. What is the speed of ball? 10 miles per hour or 100 miles per hour? How do you define it relative to the train or relative to the earth? With no absolute standard of rest, you cannot assign the ball an absolute speed. The same ball would equally well be said to have any speed, depending upon the frame of reference in which the speed is measured. According to Newton's theory, the same should hold for light. So what does it mean in Maxwell's theory for light waves to certain travel fixed speed? In order to reconcile Maxwell's theory with Newton's law, it was suggested that there was a substance called the ether that was present everywhere even in the vacuum of empty space. The idea of the ether had a certain added attraction for scientists who felt in any case that just as water waves require water or sound waves require air, waves of electromagnetic energy must require some medium to carry them. In this view, light waves travel through the ether as sound waves travel through air, and their speed are defined or just derived from Maxwell equation should therefore be measured relative to the ether. Different observers would see light coming toward them at different speed, but the light speed related to the ether would remain fixed. This idea could be tested. Imagine light emitted from one source. According to the ether theory, the light travels through the ether at the speed of light. If you move towards it through the ether, the speed at which you approach the light will be the sum of the speed of a light through the ether and your speed through the ether. The light which approach you faster than if you say you did not move or you move in some other direction. Yet because the speed of light is so compared to the speed at which you might move toward a light source, this difference in speed was a very difficult effect to measure. In 1887, Albert Michelson, who later became the first American to receive a Nobel Prize for Physics, and Edward Morley carried out a very careful and difficult experiment at the Case School of Applied Science, now Case Western Research University in Cleveland land. They realized that because the Earth orbits the Sun at a speed of nearly 20 miles per second, their lab itself must be moving at a relatively high rate of speed through the ether. Of course, no one knew in which direction or how fast the ether might be moving with respect to the Sun or whether it is moving at all. But by repeating an experiment at different times of the year when the Earth was in different positions along its orbit, they could hope to account for this known factor. So Michelson and Morley set up an experiment to compare the speed of light measured in the direction of Earth motion through the ether to the speed of light at right angle to that notation or the motion. So to their greater surprise, they found that the speed in both directions was exactly the same. Between 1887 and 1905, there were several attempts to save the ether theory. The most notable was by the Dutch physicist Henry Lorentz, who attempted to explain the result of a Michelson-Morley experiment in terms of objects compressing and clocks slowing down when they move through the ether. However, in a famous paper in 1905, a hitherto unknown clerk in a Swiss patent office, Albert Einstein, pointed out that a whole idea of an ether was unnecessary provided one by willing to abandon the idea of absolute time. We just leading a French mathematician, Harry Poincaré, that made a similar point a few weeks later. Einstein's argument was closer to physics that those of Poincaré, who regarded this problem as purely mathematical and to his dying days did not accept Einstein's interpretation of the theory. Einstein's fundamental postulate of the theory of relativity at is what is called that the law of science would be the same for all freely moving observers, no matter what their speed. This is true for Newton's law of motion. But now Einstein extended the idea to include Maxwell theory. In other words, in Maxwell theory, decided that the speed of light has a given value. All freely moving observers must measure that same value, no matter how fast they are moving towards or away from its source. This simply idea certainly explained without the use of an ether or any perhaps frame of reference the meaning of a speed of light in Maxwell's equation, yet it also had some remarkable and often counterintuitive consequences. For example, the requirement that all observers must agree on how fast light travels us to change our concept of time. Picture again the speeding train. We say that although someone on a train bouncing a ping pong ball and down may say that a ball travels only a few inches. Somehow standing on a platform would retrieve the ball as traveling about 40 meters. Similarly, if the observer on a train stood on a perch or the torch, the two observers would disagree on the distance the light travels. Since speed is distance into the divided by time, if they disagree on the distance the light has traveled, the only way from them to agree on the speed of light is for them to also disagree about the time the trip has taken. In other words, the theory of relativity requires us to put an end to the idea of absolute time. Instead, such observer must have his own measurement of time as recorded by the clock carried with them. An identical clock carried by different observers need not agreement. In relativity, there is no need to introduce the idea of an ether whose presence as a Michelson-Morley experiment source cannot be detected. Instead, the theory of relativity forces us to change fundamental our ideas of space and time. We must accept that time is not completely separate from independent of space, but in combined with it to form an object called space-time. There is not easy ideas to grasp. Relativity took years to become universal accepted, even within the physics community. It is a testament to Einstein's imagination that he was able to convert it and to his in confidence in his own logic that he worked out its consequence. Despite the overall conclusion towards which it seems to be leading, it is a matter of common experience that we can describe the position of a point in space by three numbers or coordinates. For instance, we can say a point in a room is 7 meters from one wall, 3 meters from another, and 5 meters above the floor. Or we can specify that a point is at certain latitude and longitude and a certain height above sea level. We were free to use any three situable coordinates, although they have only a limiting range of validity. It would not be practically to signify the position of a room or moon in the terms of mile north and a miles west of Piccoli circus and feet above sea level. Instead, we might describe it in terms of distance from the sun, distance from the plane of orbit of the planet, and the angle between the line joining the moon to the sun and the line joining the sun to the nearby stars such as Proxima Centauri. Even these coordinates would not be much used in describing the position of a sun in our galaxy or the position of our galaxy in a local groups of galaxies. In fact, we may describe the whole universe in a term of collection of overlapping patch. In each patch, we can use a different set of three coordinates to specify the position of a point. In a space-time of relativity, any event that is anything that happened at a particular point in space and a particular time can be specified by four numbers or coordinates. Again, the choice of coordinates is arbitrary. We can use any three well-defined spatial coordinates and any measure of time, but in relativity, there is no real distinction between the space and time coordinates, just as there is no real difference between any two space coordinates. We could choose a new set of coordinates in which say the old space coordinates were the combination of our old first and second space coordinates. So instead of measuring the position of a point on Earth in miles north to Piccoli and miles west of Piccoli, we could use miles northeast of Piccadilly and miles north of Piccadilly. Similarly, we could use a new time coordinate that was the old time plus the distance north to Piccadilly. Another well-known consequence of relativity is the equivalence of mass and energy. Sum up in Einstein's famous equation E equals to mc square, where E is energy, m is mass, and c is the speed of light. People often employ this equation to calculate how much energy would be produced if, say, a bit of matter was converted into pure electromagnetic radiation. Because the speed of light is a large number, the answer is a lot. The weight of matter converted into or just converted to energy in a bomb that destroyed the city of Hiroshima was less than 1 mole. But the equation also tells us that if the energy of an object increases, so does it mean that its resistance to acceleration or change in speed. One form of energy is energy of motion called kinetic energy. Just as it takes energy to get up your car moving, it takes energy to increase the speed of an object. The kinetic energy of a moving object is identical to the energy you must expect or just expend in causing it to move. Therefore, the further an object moves, the more kinetic energy it possesses. According to the equivalent of mass and mass, kinetic energy added up to the object mass, so the faster an object moves, the harder it further increases the object speed. This effect is really significant only for objects moving at a speed close to the speed of light. For example, at 10% of the speed of light, an object move is only 0.5% more than normal. while at 90% of the speed of light, it would be more than twice its normal mass. As an object approaches the speed of light, its mass rises or just increase even more quickly, so it takes more and more energy to speed up or further. According to the theory of relativity, an object can in fact never reach the speed of light because by then its mass will become infinity, and by the equivalent of mass and energy, it would have taken an infinity amount of energy to get it there. This is a reason that any normal body is forever confirmed by relativity to move at a speed lower than the speed of light. Only light or other waves that have no intrinsic speed or intrinsic mass can move at a speed of light. Einstein 1905 theory of relativity is called special relativity. That is because thought it was very successful in explaining that the speed of light was the same to all observers and in explaining what happens when things move at a speed closer to the speed of light. It was in consequence with Newton's theory of gravity. Newton's theory says that at a given time, objects are attracted to each other with a force that depends on the distance between them at that time. This means that if you move on that object, the force on the other one would change intensely. If say the sun suddenly disappears, Maxwell theory tells us that the earth would not get dark for about another 8 minutes. Since that is how long it takes light to reach us from earth, sun to earth. But according to Newton's theory, the earth would immediately increase to feel the sun attraction and fly out of orbit. The gravitational effect of a disappearance of the sun would have been reached its infinity speed, instead of it or below the speed of light as the special theory of relativity requires. Einstein made a number of unsuccessful attempts between 1905 and 1914 to find a theory of gravity that were constant with or just were constant having a solution with special relativity. Finally, in 1915, he proposed the even more evolutionary theory we call the general theory of relativity.